Hello everyone and welcome to Unacademy. So guys, as promised, we are on our next name reaction video and this is 17th in the series of 100 name reactions, and hopefully we are going to do it very soon. And guys, also since I am making a lot of efforts to kind of help you in making your notes on 100 name reactions, I would request you to share these videos as much as possible, because basically I'm trying to figure out the toughest part of organic chemistry for all of you. So I would definitely want this to reach out to everyone, and so that they also understand the name reaction very easily, right? Alright guys, so let's begin quickly. So Dienone Phenol Rearrangement is what we are talking about, and this is yet a very simple name reaction, but this confuses a lot of times in the exams, right? So when the MCQs are given, you might get confused in this. So let's look at it very quickly. It's an acid promoted rearrangement of 4,4-disubstituted cyclohexadienones. Alright, cyclohexadienone. What is a dienone? You are having a diene and a one like this. Okay, this is going to be the dienone. Specifically, it is mentioned for a cyclohexadienone. So 4,4-disubstituted cyclohexadienone to give you a 3,4-disubstituted phenol. So ultimately you are getting the 3,4-disubstituted phenol. Alright, so this is the whole rearrangement all about. Now what is happening? If we talk about the migrating groups, now this is a very big part which most of the students get confused, ki which group is going to migrate. As with most cationic rearrangements, what do we mean by cationic rearrangement? You have the Wagner-Merwin rearrangement, you have the Pinocolone rearrangement, you have Baeyer-Villiger oxidation. All of these are cationic rearrangement. So everything, most of the things are similar. What is similar? That which group migrates is dependent on a combination of the migratory aptitude. Definitely there is migratory aptitude, guys. The more electron rich is going to migrate to the carbocation, definitely, because it is a carbocation and it will want the more electron rich group to come to it. Yes, so the migratory group aptitude is greater for the more electron rich of the migrating group, and as well the ability of the remaining group to stabilize the resulting cationic center, that is of equal importance. I am going to explain this in a while. That migratory aptitude, you understand, the most electron rich is going to migrate, but what is the second thing? The ability of the remaining group to stabilize the resulting cationic center, that is also important. Okay, so yes, we are going to begin, and this is what you have. This is your example. Basically you started with the 4,4-disubstituted cyclohexene-dione in the presence of a simple acid. Now many a times acid is also given H plus or the BF3, the Lewis acid, AlCl3, all of these could also be given. You don't have to get confused. It's just complexing with the oxygen. That is the use of any acid, a Lewis acid or a protic acid. Yes, and the rearrangement is taking place to give you this product. Alright, so we are now first of all going to look at the mechanism, and then we are going to talk about the migrating groups. Alright, so we see that we are having two R groups. I have taken general alkyl groups over here. What happens is, guys, the lone pair of oxygen attacks on the proton, gets a positive charge like this. Okay, you can write like this also, or directly you can write a positive charge. Alright, so definitely there is a pi bond in the molecule which is going to stabilize the oxygen cation. If that happens, the carbon over here, this carbon is going to get a positive charge, isn't it? It's going to be like this, OH, and there will be a positive charge on this carbon, right? And the option is that because this carbon does not have a pi bond, does not have a hydrogens, it has two alkyl group, so one of these alkyl group is going to migrate, and this is what you get. You are going to get one of these R groups migrating. Now here I have taken both of the R as same. Here I have taken both R same, so any one of these can migrate. Let's say both of them are methyl. Okay, let's say both of them are methyl, so you are going to get the product like this, 3,4-dimethyl phenol. we're going to get something like this. Alright, so yes, after the migration step, you see that there is a proton availability. Now the proton can fall off and stabilize the carbocation by forming a pi bond, and this is how the aromaticity is regained, or basically gained in this example, because first the dienone was not aromatic. Finally you get an aromatic product. Now, so I was talking about the migrating aptitude of very many different groups. Let's say we take the R and the R dash in the beginning. Alright, so I'm just erasing to make some space. Let's say, for example, I take the R and R dash like this, two different groups. So I'm taking the methyl, and I'm also taking the isopropyl, which is going to migrate. The one which is more electron rich is going to migrate. Alright, so this is how it happens. So as you already know, the isopropyl is going to migrate like this. This is our methyl and this is the isopropyl. So I've also removed the proton and got the final product over here after this proton removal. Alright, yes, so got the final product. But if I'm asking you a question, this is very important, guys. If I'm asking you a question like this, that you have a methyl, let's say in the cyclohexane dienone, yes, dienone, you are having methyl and an ester group. So you know already that methyl is more electron donating, so you are going to draw this product. I know that in the presence of an H plus, you are going to just take away the electron density from oxygen. Here is the positive oxygen over here, OH, a double bond, and a carbocation on this carbon, adjacent carbon. So what would you think is that in the first sentence I told you that migrating group, or let's say which group is going to migrate, depends on the migratory aptitude also, but also on the remaining group. Is it going to be able to stabilize? Let's see that. Agar methyl migrate karta hai, guys, if the methyl is migrating over here like this, what do you get? You are going to get something like this. It's the OH and the benzene ring. Now okay, so there is not a double bond, just a second. Double bond is not going to be there. Alright. Yes, there is going to be a positive charge like this. Okay, and further the proton is going to be removed and then give you a double bond. But the question arises is that we are having a destabilized carbocation over here, because onto this carbocation we cannot have inductive effect of the methyl, we cannot have any kind of resonance, rather we have got attached electron withdrawing carboxylate ester group. That is why we are not going to make this product even if the methyl has a greater migrating aptitude than the ester group. What are we going to do? We are going to write the migration of the ester so that the positive charge is now closer to the methyl. It could be stabilized by the hyperconjugation effect of the methyl as well, and that is why we say that the migration of any group is a combined activity of the migrating aptitude but also the stabilizing power of the remaining group. So here the remaining group was ester if we migrated the methyl, and that is why it was making an unstable intermediate. So we are not going to migrate the methyl, rather we are going to migrate the ester, which is definitely has the less migrating aptitude. So I hope that this point is also clear to all of you कि migrating aptitude, migrating ability is a combination of electron richness as well as the ability of the remaining group to stabilize the resulting cationic center. Alright, so guys, the mechanism is discussed and the migrating aptitude is also discussed. Let's now come to examples. This is our example number 1, and if you look at the question, see, if you look at the molecule given in hand, you will be able to get, first of all you are going to get confused ki what is this. right? But then secondly, if you just draw the mechanism, and you're going to draw it by yourself by stopping the video, no cheating. Yes, so after making the carbocation, you might feel ki okay, this is just another reaction, nothing huge. Let's say the oxygen is written above, so I'm writing it above as well, and the carbon below. So there is a fused benzene ring, and yes, who is going to migrate to this carbocation? Yet again guys, if we are migrating this carbon, over here, oxygen is left out with the carbocation, and tell me, is it going to stabilize? Is it going to stabilize the positive charge? You will be able to understand this by yourself if you draw the mechanism. Always draw the mechanism. Yes. So this is what you have now. The phenyl ring has migrated onto this carbon, and there is a positive charge onto this carbon, the adjacent one, and definitely guys, oxygen is going to stabilize it due to resonance. Alright, and that is why we lead to the formation of this product. Yes. Alright, so that is why we gain the aromaticity this way, and this is the major product that we are getting. ठीक है, 80% of the product we are getting. What is the other product that you can draw? I hope that now you must have become an expert if you are drawing. Alright, the other product which is possible is going to be like this. Let me just draw the carbocation above the plain oxygen, double bond, the benzene fused ring, and yes, this is below the plane, right? So if the oxygen attacked over here, then you are going to get something like this. The methyl on this carbon, the oxygen comes over here, a double bonded O like this. Alright, or let's say a benzene molecule. Yes, so I would not say that this is a very unstable carbocation. No, there is a phenyl ring. Phenyl can also do the resonance, but when you are having the option of an oxygen which has a lone pair, so lone pair is going to stabilize the carbocation much better as compared to if you consider the stability of this carbocation. Alright, so this is a more stable carbocation. Alright, and this is comparatively relatively less stable, and that is why the product which is formed is not formed like this. This is not the product that I'm drawing, and I'm drawing it so that you get the clarity that this is not the product that you are getting. Alright, this is not correct, incorrect product. The major product is going to be right over here. So the same question, if it is asked in the method of a in the MCQ given 4 options, you must be able to understand that which is the correct option, which is the wrong. Let's say I make 4 options and I say that this is option number A, this is option number B, and in option number C I give 1:1, and in option number D I give none. This is how making options is super easy. So you must be able to write that which is the correct one, which is the wrong one. You must be able to understand through the mechanism. Alright, so now we move onwards to another easy example. Example number 2 it is. Let's see what you can make out of it. Just again stop the video, do it by yourself. So definitely it's going to take away a proton, and OH it is going to become, and further let's say guys, just looking at the stereo of the molecule that I'm just able to, alright, just drawing it again. Just by looking at the stereo of this molecule, I want to make the carbocation on this carbon. Why am I doing that? Why not on this carbon? That I'll tell you. But let's say if I generated the carbocation like this, if I move the bond like this, then there is a carbocation on this carbon. Yes, isn't it? Now I'm going to proceed with this mechanism, and one of the methyl is going to migrate onto this carbon, and you get the major product which is given in the question, that this is what you have. There was already an OH, there is a methyl, there is a methyl. Now this is the major product that you get, and you are getting 95% of the major product. Now the question is, why is this the major product? There is one more product possible. You take the same molecule, right? You take the same molecule again, and what do you see? You see that the proton, when it is getting abstracted, could be, there could be this carbon from where the bond is moving, OH, one more OH, a double bond, tertiary butyl group, and a carbocation, and these two methyl groups which are present. So I can say that the methyl can migrate on this carbon also, and it might also give us this product. Yes, yes, there is a double bond over here. Alright, it might also give us a product like this, a positive charge over here, so proton is going to fall off, and that gives you a molecule like this. So you might also make this one as the major product, but why are we not doing that? Why are we not doing that? Because the methyl which is migrating, see this part of the molecule, this right hand side of the molecule, this part, it is already bulky, right? It is having a tertiary butyl group, so this carbon is more hindered. Alright, and as compared to the left hand side, it is less hindered, and that is why when the electron density is being taken away by the carbonyl, you are going to make the methyl migrate on the less hindered side, and that is why it's giving you the major product like this. That is why this is the major product. Alright, so it's about the steric hindrance also. Steric hindrance has to be considered. Alright, this is how it is, so easy. Yes, you are getting the tertiary butyl group side more hindered, that's why you are not migrating the methyl onto that side. Okay, and on the left side it is migrating. Easy one, very easy. So now we move onwards and see one more very good example. Yes, the example is like this. What you have to do is, again you have to draw the mechanism. You have concentrated HCl, you have acetonitrile which is working as a solvent. Alright, so yet again, how is the mechanism going to be? Now, if you further want to draw the mechanism, you're just going to write it like this. Alright, just going to write it like this, and there is a reason why. Yes, it's going to be like this. So we are having this bond going to migrate onto this carbon. Yes, how is it going to look like? It is exactly going to look like this. It's just a single step mechanism over here, nothing huge you have to show. Now there is one thing that I want to tell you guys, that why is this bond migrating? Alright, this bond could also migrate, but this bond is on a carbon and a sp2 carbon, right? So the migration of the bond connected to an sp2 carbon is lesser as compared to an sp3 carbon. An sp3 carbon bond is easier to break. Alright, an sp2 carbon and a simple carbon over here, again sp3, this bond is tough to break as compared to sp3 carbon and sp3 carbon. Alright, which is right over here. So that is why this bond is going to migrate very quickly as compared to the phenylic bond. Alright, so this is your product, and this is your major product by 73%. Right, and this is what we have. We had solved 3 examples on the Dienone Phenol Rearrangement. I hope that you find the question in your IIT JAM, in your B.Sc exams, in your M.Sc exams, as well as in your GATE and CSIR exams. Alright guys, so very soon I'm going to upload a video on the GATE new syllabus as well, how to study for the GATE 2021 also. Till then, keep on studying guys, keep on practicing more name reactions, and yet again guys, I thank you so much for listening out. And if you are interested, you can join me on Unacademy Plus, where I teach for organic and inorganic section of CSIR UGC NET, and guys, a lot of good content awaits you. Also, what you can do is, if you haven't yet subscribed, do click on the subscribe button. Also like this video if you really liked it, if you are learning from this. And guys, if you think that it is worth sharing, and if you are learning any bit from this video or from any video, then please share it with your friends. Guys, do share it so that it does more good to all of you. And thank you so much once again, and I'll see you in the next one very, very soon. Till then, bye, and look in the description box for the link to my Telegram channel. Alright, for further discussion and timely notifications of all the classes, you can join my Telegram channel as well. Alright, bye, see you soon.